the probability people were interested in coming. So next week is Thanksgiving, but the week after, there'll be a speaker too.
There will.
You said, right?
Yeah, there'll be a speaker. You haven't seen Jeremy's semester or something?
No,
Okay.
I haven't seen, but I'm in my office, so it's a bit weird.
Yeah.
It wasn't here last talk, right?
No, because
He's traveling, doing some
review for Cornell.
That's right. And also I was away this summer. So I was sitting for like half the year. I went to his office.
Yeah, so I found that's what I was like, I was on Friday and I had like 15 minutes. I was like, oh, let's see if it's around.
Oh, okay.
Yeah, there's some chat. It was like,
I should, yeah, of course, like distinguished probability first. Makes sense. Usually when you have a does thing, it makes sense. So, I should have checked.
So like at one point I was like, Cameron, I can see your camera's on, like broken. And said, oh, I think about listening to you. I think.
Yeah.
Like I'm here, I just all the time. It's like, just chill.
Yeah, like.
Okay, thank you everyone for coming today. So we should have talks more or less regularly for the next couple weeks, except for next week, which is Thanksgiving. And so today we have Dante Lopez from UQAM, and he is here to tell us about the optimal time to sell a stock in the presence of defaults and volatility risks.
Okay. Yeah. Thank you for having me and for the opportunity to present. So I will present to you a problem about how to sell a stock optimally. Now, I will say as a disclaimer that I am not a financial advisor of any sort. So if you manage to find this useful and make a profit on your own, congratulations, but it's not, this is more probabilistic than actual financial. So the agenda for this talk is that I will introduce you with the motivation and the setting of our problem, that it's born from mathematical finance. I will introduce to you some introductions on the notion of Lévy processes, and then I will present to you a first version of our main result, which is not very easy to manage as it is. But then in the next section, I will show you how we were able to transform the main result using intrinsic properties of the Lévy processes into a much more manageable and more tangible way, to transform the main result into a more tangible way, and which we will be able to solve semi-explicitly, and which that will see in the revisited version of the main results. And finally, I will show you some numerical illustrations. And first of all, I would like to, this is publicity, but I would like to thank the Isaac Newton Institute for Mathematical Sciences, which hosted me and my co-author Alexander Mijatovic last year during the workshop on stochastic systems for anomalous diffusion. And part of that work was carried out during that time. So this is just publicity, and a big thank you to for their hospitality during that time. And now with that, we start with our problem. So
Why did you take a picture of the bush? It's a nice bush.
yeah, it's supposed to be an apple tree, but by the time that I was there, they had collected all the apples. So and the actual institute is is here. This is what is known. This is the Newton Institute. So if you now for the motivation, if you have ever taken any course in maybe finance 101 or even finance 0, you have heard of this phrase or adage, which is if you want to make a profit or if you want to just buy low and sell high. Now in this talk, I'm not gonna concern about the buy low part. I'm just concerned about the concept of sell high. What exactly does it mean to sell high? And in the concept of if we are investors and we own a stock, how do we know if the stock price is actually high enough to actually sell it? Now, on the one side, as an investor, like as a stockholder, you would like just the stock to reach new all-time highs all the time and as much as you want. But then there's this counterpart. If the company that's associated to the stock goes into default, then maybe you will incur into a loss because you waited for too long and you didn't sell when it was appropriate. So in this talk, we will be playing between this notion of selling the stock when it's high enough and we will propose a benchmark on how high it is, on what we mean by stock value to be high enough, and also to have this, and we will try to manage this interplay between the probability of default of the company. So in our setting, we are taking the point of view of a small investor who owns a stock. And for here, a small investor, we mean that, I don't know if any of you has dabbled with all of these micro trading apps, like Robinhood or whatever, where you can buy and sell stock. So we're in the point of view of that's what we mean by a small investor. So a person who is an outsider to the financial, sort of an outsider to the financial world and can sell stocks whenever they want. Now, this investor is informed enough to have access to past information. So at time 0, or at time now, our investor has knowledge of the whole history of this stock. And on the other hand, this stock is linked to a company that might be subject to default. And since we are taking a small outsider investor, at time 0, we do not have access to future information on default. So we are not insider trading or any of those components. So in this graph, Jesus, the color is not very bright, but on one side here we have the historical chart of the AM. I wanted to highlight a very extreme example. I don't know if you're familiar with the Wall Street bets and the AMC stock, So we have access to the whole history, and as you can see, our investor has seen that it has reached some abnormally high highs, historical highs. But then when you see today's information, you see that actually the scale is significantly different. It has traded at probably 500,000 American dollars, and now it's trading at $3. So if we are still holding a stock, and if we are holding a stock on AMC, does it make sense to wait until it hits a new historical maximum? Maybe yes, maybe not. We don't know. But at time 0, our investor can estimate a notion of the drift of this stock, and can also observe what has been the maximum value. So as a first modeling component, we suppose that, oh, I went one too fast. we suppose that the stock value is modeled by an exponential spectrally negative Lévy process. This is it is a process that has downward jumps. And this is a typo, but the current value is greater or equal than 0. And as I said, we're always tracking the current value, which is ST, and its current maximum, which is denoted by ST star. Now, as an introduction to Lévy processes, what we mean is that it is a kind of stochastic process that exhibits independent stationary increments. And for a very particular reason for this paper, we chose this special decomposition, which is a linear drift, a Brownian motion component, and a negative jump measure. So yeah, as I said, this pi is just a random Poisson random measure, which governs the frequency and the size of the jumps. With nu is as a measure that's supported on the negative infinity, highlighting the presence of just negative jumps, and satisfies this classical integrability condition for Lévy processes. And this function j is just it's part of the compensator. So as I said, I am choosing this particular formulation because we want to separate the intrinsic drift of the stock, which could be negative or slightly positive, and this other component, which we just want it to be some sort of zero mean noise.
So this J is something that I don't see at all. Like the rest of it, I understand.
Yeah.
What is the motivation for this exponential and this 1 and this theta x?
Yeah, well, J actually appears in the appears naturally in the Laplace exponent of a Lévy process. So it's just, in a way, it's the Laplace transform. Here it's just quote unquote, of course, but it's the Laplace transform or the Fourier transform of the jump component and its compensated and its compensator of the small jumps. Geez. So I'm spotting a lot of typos. So this is kind of version 1.2 of this presentation. So if you spot any other typos, that's why. So just to continue the introduction. So the law of this spectral negative Lévy process is totally characterized by what is known as the Laplace exponent, which obeys the Lévy-Khinchin formula. This function, and this is a very technical assumption that we need in most of our proofs, is that it's equal to 0 at 0. It's a strictly convex function, and so it has a generalized inverse, which is defined as this function phi of q. This is just an illustration of what we mean by a spectrally negative Lévy process, and it's running maximum here. And this is just a tricky. This is just to highlight to you that we can have access to previous values of the maximum before time 0. So normally a running maximum can start at 0, or we can start at a higher value. But as you can see, whenever we reach new maxima, this process is updating itself on and on. Now, this is the first component of our model. The second component, sorry?
Can you just go back? Just point out the jumps.
Yeah, the jumps here are, for instance, this one here. There's all of these sudden downward movements are actually related to jumps, negative jumps.
So what's the motivation for only downward jumps? Is that just like pessimistic?
Yeah, yeah. Normally in mathematical finance, people try to give more weight to pessimistic scenario, to adverse scenarios, like what happens if a stock crashes. And what it has been observed is that when people have done some econometric analysis on stocks and on volatility, they have observed that the most important component are negative jumps opposed to positive jumps. So a negative jump is actually linked to an adverse pessimistic scenario where, I don't know, some bad news happened and people overreacted and sold the stock, and then the price plummeted. So yeah, that's kind of, yeah, that's normal the interpretation of just pessimistic scenarios, and we want to capture them somehow. So the second part of our modeling is the ruin time. And for this paper, which is just basically the first approach, we chose the most simple, or one of the most simple approaches for ruin, which is known as the reduced form approach. And what it simply says is that the default of a company will be given by an exponential distribution. So once this exponential timer rings, the company will declare itself in default. And once it declares itself in default, all of the stock owners will be compensated by a fraction of the final value of the stock, which is in this case modeled by this rho of SC. And here rho, as we're supposing that we are always in the point of an outsider, small investor, both the time of ruin and this recovery fraction will be unknown to random to us, and will be independent of our entire dynamics. So, I mean, I know that some people in math finance will not agree with that, but yeah, this is what we are assuming, that we are kind of outsiders, and all of this information will just be out of our control and out of our reach.
But you know the Q and you know the rho, right? You just don't know the. Sorry, what am I trying to say? You know the law of rho.
Yeah, we know the law of rho, but still,
And you know the number Q.
yeah, we know the number Q. So that's just part of our modeling, but still they are on. Yeah, the Q is known to us, and rho, the distribution of rho is known to us. And the only constraint that we need is that the expectation of rho is bounded away from zero, just to have everything well defined in what follows.
That's also typo. The last should be an element of
Oh, yeah.
expectation of rho.
Ah, yeah. Anyway, and now, considering all of this information, we now can propose what's our benchmark for how high the stock value is. And this is where part of the interesting contribution of the problem will come from, because what we say is that we will measure our performance based on the last observed value of the stock. So no matter what selling time we choose, we will always compare with respect to the last historical maximum before default. Naturally, if we choose a time where if we miss our timing and we choose a selling time which is after the default, then we will just receive the recovery compensation. And with these two ingredients, and with a time preference factor, which is actually compelling us to sell as soon as possible, what we want to maximize is this kind of performance, which is either we are lucky enough and we pick a time before the default, or we are unlucky and we just receive the compensation. Or we make a bad choice and we receive the compensation. And if possible, we would like to characterize the optimal selling time. So as you can see from here, this formulation is kind of is non-standard because it requires us to have knowledge of the future, especially knowledge of what will happen at this default time.
Is there supposed to be a rho in that second term?
Yes, that's another typo. I'm so sorry. But yeah, indeed. There's supposed to be a rho in the second term. So this seems to be a non-standard formulation. However, this problem falls into a large category. This problem falls into an interesting category of what is known as optimal prediction times, where you want to stop the process as close to you have a signal that depends on the entire path of the process, and you want to stop as close to this signal as you can.
So it's, but you're still requiring it to be a stop.
Yeah, you're still requiring, yeah, this tau is still required to be a stopping time, but that's the interesting component of it. Tau is still required to be a stopping time, but you're measuring it against something that is that depends on the entire path. So that is actually the that's part of the interesting interplay that we are dealing with to solve this problem. So just to give you a spoiler, with this setting, we can formulate a first version of our main result, but we still cannot say much about it. So the solution of this problem is divided into 3 different regimes. So if the notion of drift is low enough with respect to this benchmark, then the optimal stopping time is 0. So we will liquidate the stock right away. However, if the notion of drift is reasonably high with respect to this benchmark, then either we will have to wait until the stock is close enough to the historical maximum, or it is optimal to just wait until the time of default, which means that we are very confident that the stock will keep growing and growing and growing. So even if the stock defaults and we receive just the recovery compensation, we will still be able to make a nice profit. So this is the interpretation of these 3 regimes. So so far this is what it this is the first version of the problem. However, with this formulation we cannot still say much about the explicit solution and even the explicit level B star.
What is S star T? Sorry, I haven't.
S star T is the running maximum, is the historical maximum. So as I said, this problem falls into the category of what is known as optimal prediction. As far as we know, one of the first instances of this comes from this paper by Coran, Pershker, and Dutoit, which is setting the stock at the ultimate maximum for a Brownian motion component. And people there is some interest in the literature to deal with these type of problems. For instance, predicting at which a Lévy process hits the ultimate supremum, or some other measure of knowing how close we are to the ultimate supremum of a Lévy process. So there is some actual active interest in these type of problems. So there's still this question of this quote unquote Markovian structure of our performance measurements, because as you can see, we are always depending on an observation of the future. So dealing with this, so part of our contribution is how we will deal and how we will untangle this dependence on future observation. So what we do in the paper is that we have this two-step decomposition, where first of all, we can rewrite this performance functional in terms of the current value of the stock and the current value of the maximum. And then we can further decompose or simplify the process as a functional that only depends on this process YT, which is the Lévy process reflected at the maximum. And once we reach this level, we are actually able to solve explicitly our optimal stopping problem using classical tools from the optimal stopping literature and using all of the properties of Lévy processes. So the first part of the decomposition is actually very easy. So with this lemma, we show that we can rewrite this for any stopping time. This performance functional can be rewritten as a function that depends on this bivariate Markov process, S tau, and the process and its running maximum at the same time. And the proof for this is very straightforward. We just have to integrate you have to take expectation with respect to an exponential time, and then after some algebra and computation and putting things together, you reach this formulation here. And that's actually not very difficult to prove. But say, if we stop here, we could already start using some Markovian, some tools from general stopping, the optimal stopping theory for Markov process, even bivariate, multivariate Markov processes. However, we can exploit the underlying Lévy structure of all this problem to simplify it even more. And what we do is that, first of all, this ratio here of ST divided by S by its maximum, we can rewrite it as the exponential of a Lévy process reflected at the supremum. And with this decomposition and using classical properties of Lévy processes, we can simplify this optimal stopping problem into a one-dimensional optimal stopping problem, which is, if you have ever studied this, if you have run across these problems, it means that we have a final reward and some kind of running cost. And all of these functions now are written in a semi-explicit way, which depends only on exponential functions, which are quite nice to deal with. So even here, this proof is more or less straightforward, just using, in a smart way, independent increments of the Lévy process. And if you have never come across reflected Lévy process in its infimum, if you recall our first simulation, here we have an illustration of how the reflected Lévy process looks like. So as you can see, whenever we are reaching a new maxima, it means that our reflected Lévy process is hitting zero, and then it exhibits these excursions away from zero, and it hits zero again when it reaches new maxima. And so this, except for these times where it hits zero, it behaves exactly like a classical Lévy process, and that actually helps us to use all of the machinery from theory to deal with this problem. So what we claim is that this problem here, 2, and which depends on the function of some 3, is much easier to handle than our first formulation.
This is a Markov process, right?
Yes, yeah, the reflected is a Markov process, indeed. So what we claim now that we can tap from all the results from optimal stopping theory, is that this function capital F that we introduced earlier, which is the solution of our optimal stopping problem, is characterized as the solution of this obstacle equation, this Hamilton-Jacobi-Bellman, which essentially decomposes our state space into two distinct separate regions, where we are actually we're not stopping, which is known as the continuation region, where we are not doing anything, or a stopping region where we say, okay, the stock value is high enough, now we can actually sell. So what we claim, and this is just from optimal stopping theory, is that the optimal stopping time is actually the first time that we enter what is known as the stopping region here. This, however, is still not satisfactory, because this is still very abstract, as in, what do we mean by the continuation, by the stopping region? And what do we even mean by having a solution of this Bellman equation? So in this final section, what I will show you is exactly that using this final version of the problem, we can actually find an explicit or semi-explicit solution of our optimal stopping problem. So if we recall, our answer says that our educated guess says that we have these 3 stopping different regimes. We either sell immediately, we wait until the stock the value of the stock is close enough to the current maximum, or we hold the stock forever or until default. So now this, and if you remember also from our first theorem, these stopping rules are characterized by these quantities here, right? So what we claim now is that these indeed are these quantities will indeed separate our three different optimal regimes depending on our parameter values. And we can actually construct the three alternate optimal solutions to our problem. So first of all, if you recall this function g, which is our terminal reward, this function will be associated with the regime of selling the stock forever. Then we define the second auxiliary function k, which is associated with the regime of holding the stock forever. And then we will define this auxiliary function v of b, which is associated with this intermediate interesting regime of holding the stock until we are close enough to the optimal, to the maximum. And what we claim here is that we can indeed find in this intermediate regime, we can indeed find some optimal selling level B star, which is explicitly defined by this quantity. And if we construct this intermediate function, B tilde, then this B tilde will be the solution of our stopping problem when we are in this intermediate regime where we sell whenever we are close enough to the current maximum. So indeed, what we can now say, and we can actually say more about about our stopping problem, saying that if our notion of drift is low enough, then indeed the optimal selling function is the optimal reward is given by this function g, and the optimal stopping time is equal to 0. If the notion of drift is high enough, but still the ratio of our reward and of our terminal reward against our initial reward is small enough, then it's optimal to follow this barrier type of strategy. And in the terminal case, then it is optimal to wait until default, and our optimal reward will be given by this function k. And I might make a comment here on the, I didn't not have it on the slides, but just a brief comment on the proof. Is that, for instance, what we can prove is that, for instance, these functions g and k that we constructed are indeed solutions of our Bellman equation. For instance, we can prove, and it's in the paper, we prove that k of z has this stochastic representation as and moreover, we prove that k of z is indeed bigger than g of z, except at 0. And that by construction, VV is also bigger than g, except on the interval 0 B star. So this is part of the proof, and the details are somewhat technical, and then, well, they're not technical, but they just rely on having some nice Ito formula expansion of all of these functionals. But what we claim here is that what we claim here and what we were interested in is that saying that if at time 0, you know that the drift of your process is high and is low or more or less intermediate or high enough, you will know exactly in what regime you're in, and then you will be able to determine what will be your optimal selling strategy. And to finalize, I will show you some examples of this. Just one example, which was very interesting, which is if we consider a tempered stable Lévy process, which is a Lévy process that has this exponential, well, quote unquote, smoothing factor, so that the impact of large jumps is not as significant. Then first of all, in terms of the model parameters, of the stability parameter and also the drift parameter, we can determine which are the three optimal regions. So as you can see, I mean, we confirmed this numerically that if the value of the stock is high enough, then you will be holding the stock forever because you're very optimistic that you will be reaching new maxima all the time. This gray region here is the this gray region here is the interesting case 2, and the darkest region is the other simplified case where the drift is low enough that you are not expecting to hit new maxima all the time. And we can actually compute we can also compute explicitly the expected reward. So as you can see, what it means here is that the closer, remember that this is all in terms of the starting value of the reflected Lévy process. So what it means here is that the closer you are to the maximum, meaning the closer you are to 0, then it is it is more likely that you will get a bigger reward as opposed to being close to the maximum and having to wait for a longer period of time to decide whether you sell or not. So
What are the axes on these graphs?
so the x-axis is the starting value of the reflected process. So being close to 0 means that you are closer to the current maximum, and being further away from 0 means that there's a larger gap between your current stock and the current historical maximum. And the horizontal and the vertical axis is the reward. It's the value of this capital F function. And so, yeah, that's basically what I wanted to tell you today. And thank you for your attention.